the previous lecture on AC circuit. Today we'll start with the Feasel algebra. Feasel algebra. Now, as far as Feasel algebra is concerned, we know that the complex quantities normally is employed in AC circuit analysis can be added and subtracted just like a complex vector. Okay. Now, if x and y axis, if x and y axis projection, if x and y axis projection of a phasor P, okay, of a phasor P are known as xp and yp respectively, x subscript p, y subscript respectively, okay. Then the magnitude p is given by xp plus yp, the square of these two under root, okay, and the angle between these two will be given by theta is equal to tan inverse it's y subscript p by x subscript p. So this is the angle between the angle between the direction of the phasor P and the direction of the positive x-axis. So that you should have an idea about. Just to distinguish between the x-axis projection and the y-axis projection, a convenient operator is used, okay, which when applied to a phasor, rotate it okay, 90-degree counterclockwise. So what we'll say is that if we'll have P, okay, or we simply write here J4P. So this will be JP, okay, this is Y, this is X. So here along this direction we'll have J square P, along this axis will have G cube P, okay. So what we can see is that turning P by 90 degree towards Y, just you multiply this one by J, P by J, and then again to 180 degree you will just multiply it by J square, further by J cube, and this. So if the operator J is apply, JA or rather JP is a new phasor, J square P is obtained, okay, that is along minus x axis, and then again J cube P is along the minus y axis, okay. So basically if it is along the negative, J square P is negative axis, so what we'll write is J square P will be equal to minus P. Similarly, what we can say is that JP is equal to minus of JP. This will be minus JP. Now, in a Cartesian form, a phasor P can be written as A plus JB, where A is the x component and B is the y component, okay, of phasor P. In fuller form, again the phasor can be written as P is equal to P cos theta plus J P sin theta. So this is the vector. So here P cos theta is the x component and P sin theta is the y component of the phasor, okay. And if the angle is measured in the clockwise direction from the x-axis, the phasor P can be written as clockwise direction. So it can be written as P, say, is equal to P cos theta minus J sin theta. Thus we see that cos theta plus J sin theta is an operator which, when applied with the phasor P along the x direction, rotated through an angle theta from its initial position. Similarly, the operator cos theta minus J sin theta rotates the original phasor through an angle minus theta. Okay, so it can also be proved that this operator rotates the phasor irrespective of the initial position of the phasor. So you can also write the phasor in an exponential form. Okay, in an exponential form, the phasor can be written as P. Okay, phasor P will be equal to P into e to the power plus minus J theta. Okay, or it could be like P, okay, and then cos theta plus minus J sin theta. This can also be written as, most of the technical book, electrical book, you will find it is written like this. Okay, so it's the same thing. Ultimately it's the same thing. Okay, so there are certain simple algebra. Addition of phasor, sum of two phasor is a sum of two phasor is a phasor. Okay, which is defined in magnitude and phase position by the diagonal of the parallelogram formed by the two phasor. So it will be like, if A and B are the two phasor, okay, it will be given by C, which will be equal to again B plus A. So it's just like A and B, so it will be given by C, the new phasor. So it's just like a addition of phasor. Similarly, we'll have a subtraction of phasor. So if we talk about the subtraction of phasor, it's like in phasor, subtraction of phasor, subtraction of phasor. Okay, in phasor algebra, phasor to be subtracted is rotated through 180 degree, and the addition is done by completing the parallelogram. So what we'll do is that we just rotate it by an angle of rotate it by an angle of 180 degree, and the addition is done by completing the parallelogram. So if it's just like this, rotate it by an angle 180 degree, okay, and then add this one, so you get the new phasor. Now we'll have multiplication of phasor. Okay, so the product of the two phasor is a third phasor. Okay, say for example, if we'll take one phasor A is equal to A e to the power J theta A, and another phasor B is equal to B into e to the power J theta B, then the product of this A and B will be given by AB, the product of the magnitude, into E J theta A plus theta B. Okay, or it can further be written as AB theta A plus theta B. Okay, so what does it mean? It means that the magnitude will be equal to the product of the magnitudes and the phase position. The phasor angle with respect to the reference axis equal to the algebraic sum of the individual phasor angle of the phasors. Similarly, we'll talk about the division of phasors. If we'll talk about the division of phasors, okay, now when one phasor A is divided by another phasor B, okay, it results in a phasor having magnitude. If A is divided by B, then we have another phasor of magnitude A by B. Okay, A divided by B, rather we'll write here A divided by B will be equal to A by B. Let it be like A by B into e to the power J theta A minus theta B. Okay, so this will be a new phasor, say for example C. Okay, so this is how we'll just divide. This is the division of phasor. So this is some of the basic algebra which is related to the phasor. Okay, then we have the Kirchhoff's law related to the Kirchhoff's law. Okay, Kirchhoff's law related to the AC circuit. So what we'll write over here is that we basically we have the Kirchhoff's law applicable to the AC DC circuit. Now here also, as there is no, number one is that as there is no accumulation of electric charge in a system of conductor, the sum of the complex current, the sum of the complex current, okay, entering any junction, okay, entering any junction equals the sum leaving the junction. So this is number one, and number two is that the sum of the complex EMF in any mesh equals the sum of the complex potential drop across all the potential of that mesh. And we can add the series impedance Z equal to Z1 plus Z2 plus Z3 plus dot dot dot. Similarly, the reciprocal of the the corresponding formula for a number of impedance in parallel, it can be found by writing the total current as the sum of the current through the impedance circuit. So in this, if it is parallel, we'll just write 1 by Z1 plus 1 by Z2. So these are the parallel impedance. Okay, and the reciprocal of the impedance is admittance. So admittance is the reciprocal of it is the reciprocal of Z, that is impedance. So y will be equal to y1 plus y2 plus so on. Okay, so in general, y is a complex quantity which can be written as y is equal to g plus js. Okay, g is known as conductance, and s is known as susceptance. Okay, so these are the two Kirchhoff's law. The second law, again I reiterate that second law is the sum of the complex EMF in any mesh equals the sum of the complex potential drop across all potential of that mesh. So these two laws basically are very much like DC current, DC Kirchhoff's law in the case of a DC circuit, but then there is a slight difference. So these are the things which we have discussed today. Next, in the next lecture, we'll start dealing with the LRC circuit in series. Okay, so thank you very much.